So now that we have these different ways of counting, what are we going to do with it? Well, we're going to get some structure. So this is the document term matrix is going to become your design matrix. This is what we've wanted, right? So literally the rows will characterize the documents, and the columns will literally be all words and possible n-grams that appear across your entire corpus. And then you're going to populate the cells with whatever you're looking at. So maybe it's term frequency, inverse document frequency. As you would expect, this can get really large, and it's going to have a lot of zeros, right? You think of all possible words. It's not going to not many of them are going to appear in each document. So you have a lot of zeros. Also, if you want to bring in that other metadata, this is how you bring it in here. So you have all your, pretty much you've created however many variables for the unstructured text. Then you can concatenate that with your structured information if you want to incorporate that into your analysis. Sometimes people refer to a term document matrix. It's nothing fancy. It's literally just the transpose of this. So the rows are the terms, and the columns are the documents. Don't get confused. They're not doing anything fancy. So how do we make a document term matrix in R? Well, first thing you should always do is strip all the white space, because this is where you're really going to tokenize. And you notice when we remove words, sometimes it would leave white space. When we tokenize, it's going to think white space. If you have 3 spaces, there's a word in that white space. There's nothing there. Strip it down. It puts 1 space in between all of them. Sometimes these mapping functions in TM can change the that's the class of the actual documents. They need to be what's called plain text documents to be read into the document term matrix. So just at the end, just apply this across all. It's easier. It might yell at you if you don't. And they have a very nicely named function called document term matrix, which you apply to your corpus. If you want to, believe this is stored as a sparse matrix, so you can't just look at it directly. You can set it as like as.matrix and look at it, but it's easier to just look at inspect. And what it's going to do is give you some information. So we have 2 documents, and there's a total of 11 terms across all our documents that we looked at. We have, of all the 22 cells, 15 of them are non-sparse, and 7 of them are just 0. So we have a 32% sparsity rate, which is really, really low for a document term matrix. Usually you're up in the 80s to 90s. The longest word is 8 characters, and what we're characterizing in the cells is the term frequency. And so you can see it's literally, we only have 2 documents, and you can see, so it counted. So line appears in both of the documents, yard appears in both, but remember the one was about the Steelers, the other was about the Seahawks. This can get really big, so one thing you might do is set some type of threshold. So let's say, I don't want any word that only appears once, because that's really not going to help me at all. So let's say I want a word that has to appear twice. This control list has a lot of options. It's like a list inside a list for the bounds, and I'll now keep any word that at least appears 2 times all the way to infinity. You could also put a maximal bound, thinking that the inverse document frequency is pretty much going to shrink everything to any word that's used a lot to 0, so just remove it altogether. Who needs it? Here we only have 2 documents, so it has to appear in both of them, so these are just the common terms between them. But this is a way if you want to set some bounds to at least just start by not having such a big matrix. Another way to do this, because this can be slow if you have a lot of data, is to take your original one and do this remove sparse terms. So these will get rid of any term that has a sparsity 50% or greater. So then you're just working on the document term matrix you already built, as opposed to rebuilding one and then throwing things out. So you can save a little time if you want to do this. And this is the exact same matrix as this one. So we talked about the weighted document term matrix. How you get to this point is you do this function, which I always misspell, weight TF-IDF on your document term matrix, and then this will apply this weighting. So keep in mind this, it's going to normalize, so each term, the term frequency is just a percentage of all other documents, but you can see any term that appeared in both documents is going to be 0, right? Because we're taking the log of 1 then. And then we have, so now these words are sort of weighted. It's hard to really get when you only have 2 documents, but this actually works really well once you do this. And they actually have this really cool function. It's called smart weighting, where they, in the help, characterize this formula that has different parameters in it that you can do different types of weighting by setting them to different things. So imagine sort of how binomial distribution works. You set it to 1, it brings in this part and cancels out all this other stuff. It's a similar idea, but you can really get your own, you can weight things however you want and do your own frequencies. So you can really get at what do you think is the best way to characterize this information. If you want to do n-grams, it's not built into TM, so we have to bring in Weka. This is just a function I wrote. Again, we call Weka directly. So this is going to do all single words and all double words. So you set your tokenizer, and now you can see we've enumerated all 22 n-gram or 2 grams in this. So now you see, so things like yard line might be important. Okay, Jerome Bettis, we now can look at that interaction as opposed to just the individual words. Okay, so you can get a lot with this, and again, you're probably going to have to throw out a lot of stuff because some words are just going to be nonsense. You probably want to get your sparsity in there. Last thing I really want to cover is what you do when you have training and test data, because it always annoys me when you look online and they talk about doing text analytics for like a spam filter, where you think of the idea you're going to have some training data and then a new email is going to come in and you have to classify it. Well, what they always do is they take all the data, they make a document term matrix, and then split that into test and training, which really doesn't characterize how you would do it. And you're incorporating information from the test set into the training set then. It's just not how it should be done, right? You can see sort of the circular thinking of that. So let's say I have some fake spam emails, and I have some fake test spam emails that I want to then classify after training. I just lowercased everything so it's easier. You can actually get a lot of, like I said, like we remove stop words. In this control, you can like remove stop words, remove punctuation, so you can reduce your code a lot. You don't have to do all those things, keep applying it. These are all the different terms that get pulled out of our training set after removing our stop words. Then what you can do is actually, you can make a document term matrix, but set all the words it looks for. So it's not going to pull the terms from the data. It's going to have a dictionary that it's then literally just going to count or apply a weighting to. So this is then, you get a new email in. I really just need to populate a row, what it would look like. Imagine if we even had structured data, it would be the same idea, so I can then apply my model to it. And this is how you can do that easily. Just I want to point out, because it's never really, it's always done wrong online. That always bothers me, because otherwise you would have to bring the data in, build a huge matrix, refit a model, and then classify, which doesn't make sense to do. Probably want to update every once in a while, but you can see now we have much higher sparsity.